Oh, okay. Yeah. I wasn't recording, so sorry about that. Okay. And finally, okay, we can see again, let me talk about the D flip-flop. Okay, let me just talk about the JK flip-flop once more. Again, this one is not clocked. This is the one we want to transfer to. This is the one we want to transfer to. So if J is 1, sorry, if J, we know how the J flip-flop works. J is 1, K is 0, that is set. J is 0, K is 1, that's clear. Now let us assume that we don't care what B is really. Let us assume that assume A is equal to 1. If A is 1, that A is at that line. That means also that J is equal to 1. Now, obviously, if A is 1, then A inverse is 0, meaning that K is 0. Now, this will be 1, and that will be 0, meaning that this flip-flop B is set to be set, but it is waiting for the right clock transition. So the moment you get your NGT, this one, basically this thing will be set, meaning that now B, you can say after NGT, B will become 1. And as you can see, you had a 1 here, which was saturating here. Now B is also equal to 1. This is similar to transferring what was at this point to that point. And the other way around also applies. If A was a 0, that means J is a 0, making K is a 1. And so after NGT, if you had a 0 here and a 0 here, if you had a 0 here, after the NGT, what happens is that 0 and 1, obviously if you have a 0, you have a 1 here. Now this is going to reset by making B equal to 0. And so after NGT, B becomes 0. And this is similar to you moving that 0 and storing it in the next flip-flop. So these are called registers. And when we transfer information from one flip-flop to the next, what we have done is called data transfer. But this is a synchronous process. You must first wait for the right clock transition to happen before information is transferred from one flip-flop to the next one. In this case, we can see that we are moving information from the left to the right, but we can also move information from the right to the left. And the D flip-flop is really easy for it. You just connect this, once again, the A output to the input of the next D flip-flop. This one is not connected, of course, because the D flip-flop has just one input. So, or one data input, so to speak. So this again is not clocked. Now, the moment this is clocked, what is at D will move to B. So imagine you had A was equal to 1. If A is equal to 1, it means that all this line has 1. The moment you clock, this one is moved to there, which is essentially similar to transferring. Now you might ask yourself, what happens to the data which was at B? It will be flashed out. In real systems, that data will be moved to, just a second. Just 1 second, let me sign something small here. Sorry about that. So yes, I think we had pretty much finished this. So this is called data transfer. We are going to look at bigger schemes of data transfer. These are just, we have basically here, we've been moving just one bit, but we are going to look at how we can move a number of bits across registers in this course, in this, maybe not this lecture, but in the next lecture, certainly. But also we look at this again sometime in third year. Let us look at asynchronous data transfer, because what we have seen here is synchronous data transfer. You can see we've been using the clock, but we can also transfer information using asynchronous data transfer. In this case, we take advantage of the pre and the preset and the clear. So if you can see here, what we have here is we have an AND gate and an AND gate here. We connect them through through to the clear input and also the preset input. You have your J and K inputs. You can connect whatever you want to connect to them, and also the clock inputs. You can also even clock, if you want, you can clock these, but we know that the preset and the clear inputs are called overriding inputs. So even if you're clocking or whatever, these inputs will not care. These asynchronous inputs will not care about your synchronous inputs. They will override them. So anyway, let's see what happens. Now we need to make sure that the transfer enable input is enabled. So if we have a T, our T here, and we can have A here, that means here we have A inverse and again T here. And that means at this point, our input, which we can say clear, which we can put with a bar, is equal to A inverse T. And here, our pre is equal to AT, A and T, basically. Now, we want to see how this data transfer is happening. T should be high for data transfer. Okay, it is, so T is active, high. Now, assume A is equal to 1. If A is equal to 1, what is preset? Because T is already 1. So if A is equal to 1, you have 1 and 1, which is 0. And here you would have, if A is 1, that's a 0 and 1, which will give you a 1. So you would have a 1 here and a 0 here. And we know that what happens to B? B will become 1 because we are presetting. If you have a raw input into the preset, which is an active low input, what you have is you have set the flip-flop, and so B is 1. Now this is equivalent to moving your A, which was 1, to B. You can see that A, which was here, has actually been transferred to the next flip-flop, but via an AND gate as well as the preset input. Now, what if A was a 0? If A is a 0, then a 0 and inverse of a 0 is a 1 and a 1, which gives you a 0, meaning that now instead of having a 1 here, we have a 0 here. And here we would have A, which is a 0, and 1 giving us a 1. So instead of having a 0 here, now we have a 1. You have a 0 here and a 1 here. If this is the case, we are going to clear the flip-flop because clear is active low. And so if it's a 0, it will clear. Preset is active low, so because it's 1, it's inactive. And by clearing here, B is becoming 0. So this is equivalent to transferring your A0 and storing it in that flip-flop by making B equal to 0. So you can see how in asynchronous terms, data transfer actually happens. Any questions on this? Vivian?
Morning, sir.
Good morning, Vivian.
My question is about the presets.
Yeah.
And the clear. You said for preset is equal to A and then for clear is A bar and T.
Yeah. Oh, by the way, this is strange.
But when we are getting our
the NAND. I may have messed this up actually. Let us have another look at it. I don't, by the way, know your question, but I've seen something quite funny. Let me just make sure that I've got this correctly.
What was the question?
That was the question. So our NAND gate, in this case, pre is equal to, we have said this is A and T. This is A, this is T and A inverse. So we are going to have A and T inverse, but we know how a NAND gate operates anyway. Okay, so that is an AND gate. And also this is an AND gate. So we are going to have A inverse and T. Isn't that an AND gate? Yes, that's an AND gate. And that is our clear. And that's our preset. Okay, so Stephen, make sure you get this correctly. Now, yeah. Okay, so let us look at whether I bungled this earlier. Now, if our A is equal to 1, okay, that means A is 1 and T 0. So you would have a 1 here and a 0 here. If you have a 1 and a 0 here, we know that preset is equal to be 1 and 0 inverse, which would look like a 1. But I am asking, but I think yeah. But if we have an AND gate and we are okay, we are getting a 1 actually. So we get a 1. That is very strange. Yeah, we get a 1 here. So a 1 and a 0. When we put this through the NAND gate, let me just put it. Sometimes these things also confuse me, by the way. I know you don't believe it, but I have to think. So NAND A, B, X 0001 1011, and so we know that this is a 1. The moment you have, yeah, that is a 1. The moment you have no, that's a 1, and that is 0 0 0. Musa.
Good morning, doctor.
Good morning.
I thought like when we use 0 as the transfer enable, aren't we disabling
if we use a 0
when T0?
If we use T0. Oh, okay. So that is the issue. Yes, this is where actually I got it wrong. Yes. So T should be equivalent to 1 actually. T should always be equal to 1 because it is active high. Thanks for seeing that. That's what was confusing me. So you have a 1. This would give you a 0. Okay, that's where I was getting it wrong. So the T should always be equal to 1 if you want to transfer. If you don't want to transfer, you make it a 0, obviously. And so we are saying that A is equal to 1, which gives us a preset of 0. Now, when A is 1, the clear, obviously here will be, if A is 1, that will be 0 and 1 with a bar, which is actually 0 with a bar, which is a 1. So clear will be actually 1 and preset will be 0. And we know that when our preset is 0, we are going to have B equal to 1. So our 1 at A actually somehow ends up in that flip-flop, and that is data transfer. If we look at case 2, where A is 0, if A is 0 here, our preset will be equal to A, which is 0, and T is 1 with a bar, which is actually 1. and our clear will be A inverse, which is now a 1, and the 1 with a bar, which is actually a 0. And we have a clear input of 0 and a preset input of 1. That means clear is active. And when you have clear 0, you get B is equal to 0. So in other words, your A still finds its way into that flip-flop, and that is asynchronous data transfer. The idea of asynchronous is that in this case, the moment you apply the transfer enable, the 1, things happen immediately. They don't wait for the clock. Abraham, is it still wrong? Isn't an AND gate not AND? Daniel says, I don't know if you're saying that my NAND. Okay. So 0 and 0 should be equal to 1. Anyway, that is 1. That should be 0. 1 1. Okay, so I think that is the correct one. That is the correct one. Yeah, 1 1 1 0. Doctor, it's a bubble to bubble, doesn't it act like an AND gate? Who said that a bubble to bubble acts like an AND gate? An AND. Not Joseph. Bubble and bubble do not create an AND gate. So the data to be transferred is the one that is passed through the transfer enable, or it's grounded to get a low and fed it with the one to get a high on the transfer enable. No, the data that is transferred is the data at A, because remember this, I told you that the data stored in this flip-flop is the state of A. So if A is 1, that is the data that is stored at A. And you remember I was drawing this. So this A will come and somehow end up there. And this A will come and still end up somewhere there. The transfer enable is just an enable. It's a control input that enables the transfer or not, or disables it. Okay. Now let us look at parallel data transfer. What we have seen here is actually serial data transfer. You can see these are arranged in serial data transfer. So if I wanted to add, I can have one flip-flop connected to the next flip-flop, connected to the next flip-flop, connected to the next. I can add as many as I want, and this is serial data transfer. In parallel data transfer, you have your registers stored, arranged in this way, in a column sort of. Okay, so in this case, you can see we have 3 flip-flops, and here we have 3 flip-flops also. Each flip-flop is connected to the next flip-flop. Obviously, this creates a word that is x2, x1, x0, where x2 is the most significant bit and x0 is the least significant bit. This is the destination register y2, y1, y0, where this is the MSB and this is the LSB. So in this case, obviously you want to transfer the most significant bit. Okay, so if you have x2, x1, x0, if you're transferring this information into that, you want this to replace that, the one in the middle to replace that one, and the least significant bit to replace the least significant bit. Because imagine if you're transferring the values 1, 0, 1, 1, when you transfer it into a new register, you want it to also end up there as 1, 0, 1, 1. It shouldn't end there as 1, 1, 0, 1, because this is a totally different word. Okay, so that's why we connect the most significant bit here to the most significant bit flip-flop, the one in the middle to that one, and the least significant to the least significant flip-flop. Now, the other thing in parallel transfer is that all flip-flops are clocked simultaneously. Okay, so that means we use the same clock. You can see you have a clock here. It is going in there, it is going in there, and also going in there. And it is a PGT in this case. We don't have to clock these ones, by the way, because In this case, we are transferring information from them to the next one. We just need to clock the ones that we are transferring to. Now imagine that D2 is a 1, D1 is a 0, and D0 is a 0. We don't care what is here. Whatever was there, it will be flashed out. The moment we get a PGT, this information, 1, if you have a 1 here, then it means x2 is equal to 1. If you have a 0, it means x1 is a 0. And if you have a 0 here, it means x0 is also a 0. So the moment you get your PGT, this 0, which is also circulating along that line, and this is a D flip-flop, will transfer to y0. This 0 will transfer to y1, and this 1 will transfer to y2. And that is parallel data transfer. Because all these are clocked at the same time, the transfer into them happens all at the same time. Okay, I don't know if you have any questions. Okay, so me, I have a question for you. Let me assume that initially, Kasaja.
Yes, doctor, thank you. I'm sorry to take you to the other previous slide. This one I've understood, but I'm getting confused of that bubble at this last flip flop. That bubble at the clear and the yes and yes. The pre. It is confusing, isn't it? Affecting our input from the NAND gate. Sorry,
no, it is not. It is. No, it is not. It is basically just saying, or you could say, is it affecting? I think, let me just draw it here. It is basically saying that you can see that when you write your pre, on the inside, you don't put a bar because there is a bubble. So the idea is that the information coming, if it is to be active, the information coming from up here should be 0. So if I'm writing this on the outside, I have to write it as pre with a bar. And that tells me that actually that input is active low. When a 0 is coming in, it will be inverted into a 1 and it will perform whatever it performs. But we are looking at it. Yeah, you're making noise for us. But we are looking at it from the outside. As long as I have a 0 here, I don't even need to worry what is this bubble is doing to my input. It just means that it is the active state. 0 is the active state because we have a bubble. Musa? Musa?
Yes, doctor. Can't I do that like me? What if I don't say pre-bar like, and I say if I have for the first flip flop, if I have that A, and A comes to the input of that NAND gate, like it is A and 1 because it is 1. And I say,
yeah, you can say A. You can just say.
And I say at that output I have A inverted. Then I invert it again to say pre is A, and then that A will be transferred to B. Like
exactly.
That.
So essentially that is what it is. It's just that we were looking at the first equation. For you, you have done further analysis, having known that actually T is a 1. What Musa is saying is that since we know that we have pre, me I had pre is equal to A, and T inverse because you have it is an AND gate, so you have inverse. Now we know that T is equal to 1, so we can say that pre is actually A inverse. Okay, so that is A inverse here at that point. And if you go around the bubble, now inside here in the flip-flop, now your pre becomes A because of that bubble which converts it. And so, yeah, it just means that if pre is, if pre is A, if you have 1 here, it will just be transferred to that. I would say that for the majority of you, that if this analysis is difficult, all you need to remember is that if you have a bubble here, you better be having a 0 coming into that bubble. If you have a 0 coming into that bubble, that is the active state. If you have a 1 going in, that is inactive. It is not going to do anything. What these guys are trying to do is look at the inside. And I'm just saying that that might confuse some of you. Okay, so I had a question for you since you don't have a question. We are in this parallel transfer. I have my x2, x1, x0, which is 1, 0, 1. Okay. After 1 pulse, what is y2, y1, y0? We could say that y2, this is initial. y2, y1, y0 was 0, 0, 0. After 1 pulse of the clock, what is y2, y1, y0? Yeah.
I think it's 1, 0, 1.
That's for J.
Yeah. Thank you. So let's use the chat so that too many people don't speak. But if you see your answer has been typed in there, then you don't have to type it again. But Louis has typed 101, and the guy who spoke also gave us 101. That is correct because the information that is here after the first pulse has been transferred.
K0, so that is the set state, but I'm only in the one state, so I will.
Sorry. Now, what about x2, x1, x0? What are they now? After the first pulse. What is x2, x1, x0? I'm looking in the chat.
Oh, 0, 0, 0.
Musa. Musa. Why, Musa, why do you say 0, 0, 0? Or nothing there? If you're typing 101, we have already seen it. In fact, the truth is the answer is that it's 101. And there can't be nothing there because the information wasn't deleted. By transferring information, you're not deleting it. Remember, the information here will stay. It's just a copy of it that has been transferred here. The reason why it stays is that these are not clocked. If these were clocked, together, then the information at their inputs would have actually replaced that one. So I could have said, imagine this is 0, 0, and 0, and you have also a clock. But if you don't clock these flip-flops, the information in them will stay. But a copy of it can be transferred by connecting these to the outputs. Okay. Okay. So that is the explanation. Now I want to ask, after two clock pulses, what is x2, x1, x0, and what is y2, y1, y0? Yes, both will still be 1, 0, 1. Because the same information is still at x2, x1, x0, so the same information will be transferred to y2, y1, y0. The previous information, which was also 101, will be pushed out. Okay, you can see arrows here. But the reason why they are still the same is because it is still the same information that is being transferred. Actually, the first couple after pulse 1 has been pushed out. It has just been replaced by a new couple of the same because x2, x1, x0 has not changed. Is that very clear to you? I hope that it is very clear. And we can move on. We are going to use why I'm sticking to this because we are going to be using. Yeah, we are going to be using these principles in the next slides. Now, I'm going to make a copy of this slide, and then I'm going to delete this because I'm going to use it for. Mariam, if they are clocked, okay, we could do, let me, for instance, yeah, let's actually do that. That's okay. Would be interesting. Right. Now we are going to say here that we have clock inputs. We have D clock, D clock. And our clock is going to be, it can actually be the same, okay? So let us connect this to the same, okay? Now let us assume that here we have a 0, a 0, and a 0. In other words, these are sort of grounded. It means the 0 is prevailing at all times. Now, we can say pulse. We can say x2, x1, x0. By the way, x2, x1, x0 is the register x, and y2, y1, y0. So before any pulse, we can say that x2 was 101, and we can say that y2 was, yes, y register was 000. In other words, it means that there is information in x that is 101, but in y, the register is actually cleared. Okay, so there is nothing there. We have already seen that after the first pulse, this information is transferred in parallel to that information, to that register. The information in x will be transferred in parallel to the information to y, to register y. So we have a 1, 0, 1. What do we have at x2, x1, x0? What will be in x2, x1, x0 after the first pulse? I need more trials. I've seen Julius, I've seen Musa, now I see Kasiswa. Kasiswa says 000. Any other trial? 000, say a good day. Patricia 000. Okay, Charles 0000. So in fact, thank you. The answer here would be 0000. The reason is, okay, so the answer is 000. For once, we have all sorts of answers, but the answer is 000. You can stop chatting. The reason is because now, because we are clocking also the x, this information that was here, once it is transferred here, this information at the input actually replaces it. The issue is that before we were not clocking the x's, so their inputs were not transferring actually to the outputs. But now we are clocking it. So the moment we clock it, what is at the input will transfer to the output. But because we are clocking them simultaneously, once this information actually goes there, this information just replaces it there. What about after the second pulse? What happens? After the second pulse, this information will transfer here, which is 000. And because we still have our 000 at the inputs, it will simply transfer into the X register. After the third pulse, this information will transfer here, but the 00s at its inputs will transfer there. Obviously, if we change these, we are going to see a difference. But at this point, if you don't change the inputs, it will continue like that. I hope that is clear. Okay. I hope that is clear. Thank you. I think that was Ndajiri who asked that question. So it has helped us too, because you can see some of you didn't understand this. Somebody who is Miriam Nagai. Okay, let us look at this. So now I believe that now we are using JK flip-flops. This is called a shift register. A shift register is not similar to this one. Okay, you could say, I mean, we are shifting information from this to that, but a shift register essentially is where we arrange flip-flops so that information shifts once every clock signal. Okay, so every clock interval, we shift once. And the next clock interval, we shift again, and the next clock interval, we shift again, and so on and so forth. So the information will move from one flip-flop to the next. If you have your flip-flops, and so on, if I have information here, say a 1, and I want to transfer it to this, I need to give 1, 2, 3, 4, 5. I need to give 5 clock pulses, because the first clock pulse, it will come here. The second clock pulse, it will come here. The third clock pulse here. The fourth there, and the fifth there. It is similar to when you are working with your calculator. When you're pressing, you see that the numbers are moving, you know, leftwards. If I press a 1, it will type here. If I press a 2 now, the 1 shifts here and I have a 2 here. If I press a 4, now the 1 shifts here, the 2 shifts here, and I have a 4. So this is the same concept that you can shift information. So in other words, this 2 replaces this 1, pushes it away. This 4 pushes 2, 2 pushes 1, and so on and so forth. Same to your computer. This is how these displays actually operate. So let us look at this diagram, which is based on JK. This is your data input. And here, of course, the data can be 1 or 0. Okay, so and its inverse can be 0 or 1. It's simple as that. You can see we have shift pulses. In this case, they are NGTs. Okay, so NGT. Every time we have an NGT, we shift. So let us do a simple truth table pulse. We are going to do. Now you can see that the input here, the data is being fed into X3. So X3, X2, X1, X0. 0, that is initially, 0 is initial. We can say that they were cleared. Even if they are not cleared, it is okay. Actually, I need to know where the information was being put in here. The data is 1011. Okay. So the data they are giving us is that I need to remove this. Okay. The data we have been given is 1011. Now we always start with the least significant bit because you want to move your data in here. This is your LSB. This is your most significant bit. So that by the time you're done shifting, your MSB is here, your LSB is here, which is X0, and MSB is X3. So that is why we start with the least significant bit and we put it into the shift register. So initial, and I'm going to put another table here and say D. Okay, so D, initially, there is no D. After the first pulse, at the first pulse, my D should be 1, which is the LSB. No. Just bear with me briefly. Okay. Okay, so initially my D input, the input D that I have here is a 1, which is the LSB. Now, after my first pulse, why I've changed this is because I want by the time the pulse comes in, the right D input is already there, applied. Remember the setup time. Okay? So you need your input there before the clock signal comes in. So the moment my D comes, my input D is there, and I get my first pulse, what actually happens is that this D, which was a 1, is shifted into X3. That is why we say shift. That's why we call these shift registers. So this will be shifted here. And this 0, which was in X3, will be pushed into X2, because remember, X3 being 0 is here on this line. So if we clock, this 0 comes there. So this 0 will be pushed here. that 0 will be pushed here, and the 0 in x1 will be pushed into x0. Now the 0 in x0 is basically discarded. Now it is discarded. It might go into some other part of the circuit, but here, because of the circuit, our circuit ends here. That's why we say discarded. Now on the second pulse, my D should be, you could actually put it here. Really, it doesn't matter. My next D is now this one, that one, which is, I could say D3, D2, D1, D0. So let's use that. This is D3. We can say that when our second pulse comes in, our D2 is the one which is there, and D2 we know is a 1. So it means that this one now will go into X3. The one which was at X3 will go into X2. The 0 at X2 will go into X1. And the 0 in X1 will go into X0. Oh, this is 0 actually. And that the 0 here, which was there, will be discarded. Now on the third pulse, we should have applied our D1. Our D1 is actually a 0. Okay, D1 is a 0. So if a 0 is here, when the clock comes in, this 0 will come to X3. So we have a 0 here. This one will push into X2. That one will push into X1. The 0 here will push into X0, and that 0 will be discarded. On the fourth pulse, we have D0, and D0 is a 1. So that 0, when D1, this 1 comes there, the 0 here will be pushed forward. So 0 comes there, this 1 comes here, and that 1 comes here, and that 0 is discarded. So you can see that after 4 pulses, X3, X2, X1, X0, which was initially 0, is now 1, 0, 1, 1. And so we have transferred our information 1, 0, 1, 1 into the shift register. Obviously, if we keep clocking, this information will be pushed out. But if you're transferring 4 bits, you need to know that you need 4 pulses to fully transfer that information into the register that you want. Now, if we were doing parallel transfer, we would transfer all these bits using 1 pulse, as we have seen in this case. But we would need to arrange our flip-flops and registers in this manner. Okay. Dion requests a pardon. I'm going to do that. Excuse me, doctor, isn't the arrangement of D3, D2, D1, and D0 flipped? It might be. I'll just look at it again, just as I explained to Dion and others who have not got this. Okay. Okay, so one more time. Pulse, D input, X3, X2, X1, X0. So our first pulse at 0, there's no input, and our pulses are our register has 0, 0, and 0. It is initially cleared. After the first pulse, when we apply the first pulse, we need to have our D0. Remember, D3, D2, D1, D0 is equal to 1, 0, 1, 1. I don't know what Pascal was talking about, but we are just doing examples. Let's take it as that. It's okay. So it means that we need to apply the least significant bit first, because we need to push it through to the other least significant side of the shift register. So D0 being a 1 means that this one will come into X3, because by putting it here, it means you have a 1 here. Here. So when you get your clock signal, it pushes this one into X3. What was at X3 push goes to X2. So that goes here, that goes there, and that goes there, and that one is discarded. Now, on the second pulse, you are applying D1. Oh, I see what you are saying. Yes, this arrangement was flipped. Okay. You have D1, and D1 is also a 1, so it will push here into X3. Now, what was at X3 goes to X2. What was at X2 goes to X1, which is a 0, and what was at X1 goes into X0, and that one is discarded. And then you have your third pulse. When you have your third pulse, you better have applied D2, and D2 is a 0, so you have a 0 pushing into X3. What is at X3 should go into X2. What is at X2 goes into X1. What is at X1 goes into X0, and what was previously at X0 is discarded. And for your fourth pulse, you are applying D3, which is a 1, so that one comes into X3. What is at X3 goes into X2. What is at X2 goes into X1, and what is at X1 goes into X0, and what was at X0 is discarded. So you can see that we have transferred our information D3, D2, D1, D0, 1, 0, 1, 1 into our shift register X3, X2, X1, X0. But because we are using 4 pulses, because we are using a shift register, in other words, serial transfer, we need more pulses, and the number of pulses you need is equivalent to the number of bits that you are actually transferring. And obviously, I don't know if the book has the truth table, but you can see when you do the truth table, it simplifies things. In fact, what the book has is this. And you can see that X3 becomes, I don't even know what this is, by the way. Okay, so the data is 1, 0, 1, and 1. And you can see this one prevails, I think, because of the hold time. And so X3 will first of all become a 1. You can see X3, if you follow X3, it becomes a 1, a 1, a 0, a 1. And so that's why it is, I see a 1, a 0, a 1, and a 1. It's interesting. You have a look at this, but you can also draw this really if you wanted. Let me see how we can draw it if we want. Okay, I'm going to remove that and also that. And then we can say that, we can say that we have clock pulses. This is the first clock pulse, second clock pulse, third clock pulse, fourth clock pulse. And we know that X3, X2, X1 is X0 are initially 0, X3, X2, X1, X0. So X3 is initially 0. At the first clock pulse, it will become 1. At the second clock pulse, it will remain 1. At the first, the second, the third, it will go to 0. And the fourth, it will go back to 1. X2 is at 0. It will stay at 0 until the second clock pulse, when it becomes 1, and it will remain 1 until the third clock pulse, when it goes to 0. X1 is going to be 0 through the first. X1 is this, so 1, 0, 0, then 1. It is 0, 0, 1, 1. So the first clock pulse is that one, it is 0. The second clock pulse is that one, it is 0. Then it will become 1 on the third clock pulse and continue at 1. Then X0 will be 0 all the way to the 4th pulse, at which it actually becomes a 1. So if you want to draw your things, you can actually take them from the truth table. And if you notice at the 4th clock pulse, if you want to see the state at the 4th clock pulse, if we are starting at x3, x2, x1, x0, it will be 1, 0, 1, 1, which is 1, 0, 1, 1, which tells us that our information has been transferred fully. At the 3rd clock pulse, no, this is the 3rd clock pulse, it will be clearly 0, 1, 1, 0, okay, which is the same as 0, 1, 1, 0. Anyway, there are so many things that you can do with this, but we are interested in transferring our information. So we are looking at the end of the pulse. Okay. Any questions? So I think what we are seeing here is 1, 1. No, that is data in. That's 1, 1, 0, 0. So I think in this, they were transferring 1, 1, 0, 0. You'll have to check and see when you are reading, because I don't remember what the book says. Do we have any questions? If there are no questions, let us continue. Musa?
Yes, doctor. No, that one, I think the X naught isn't it a 1?
X naught is a 1, yes. 1, 1, 0, 1. Yeah, that's a 1, sorry. So we were doing 1, 0, 1, 1. I think they were doing 1, 1, 0, 1. Okay, that's okay. Thank you. And of course, you can see they also started off cleared, 0, 0, 0, 0. Okay, so I think you get the gist of what we are doing here. Now, what we need to see, okay, so let us look at parallel transfer. Here we have seen how we can shift information. This is a shift register. Here we have 2 shift registers. In fact, we want to transfer our information from register X to register Y. Okay, so you can see register X is made up of D flip-flops. We have 0 here, and register Y is made up of D flip-flops also, but everything is clocked together. And this is an NGT. So you can say, we can say pulses, we can say D in, we can say, by the way, we had some, no, but it is not very difficult or very different from what we've already seen. Y2, Y1, Y0. So before the any pulse, our D input, there is no, we can assume no input. We can even say 0 because there is no in anyway. And I think they are saying that X was initially 1, 0, 1, and now Y is cleared, initially cleared. Didn't we do something like this? Yeah, we've already done something like this, which is really nice. Thanks. So the first pulse, our D input is a 0. Okay. So what happens is that 0 goes into X2. You can see here that if it's a 0 here, it just goes into X2. And usually they will keep this at some value like a 0 or a 1 or something. So you have now a 0. This one goes here. That 0 goes there. Now this one, remember now X0 was a 1, but this one is saturating here. So it's the first one that makes the jump and crosses into the new register. So this one will actually now cross and come here. That 0 goes there, and that 0 goes here, and that 0 is discarded. On the second register, on the second shift, again we have a 0. Meaning this 0 replaces that 0, this replaces the 1, and that 1 replaces the 0. This 0 crosses over, comes here, that 1 goes there, that 0 comes here, and that 0 is discarded. On the third shift, On the third pulse, again, we have our input as 0. It pushes into here. This 0 comes here. That 0 comes here. This one crosses over to there. The 0 comes into that position. The 1 goes to the receiving end position, and our 0 is discarded. So you can see that our information has now been transferred from the initial start to this point using 3 pulses. The reason why it is 3 pulses is because we have 3 bits we are transferring. The other consequence is that now we can see that X actually has 0, 0, 0. And the reason is because the input to the first D flip-flop was 0. So this is how you really arrange registers, serial registers. You get one flip-flop, you connect its output to the input of the next one, and you make sure you clock them together. Any questions? Okay, so Nsozi has a question. I think the initial D value should be set to the LSB since it doesn't wait for the clock to get an input, and the input is already available, only waiting for the parsing for shifting to start. It should be set to the LSB. I don't understand the first part, but the second part sort of makes sense. But what we've done is actually the right thing. If your suggestion also does exactly the same, much as I've not understood it, it is okay, because with digital electronics, it's all about logic. Things can be done differently, but as long as they are done logically. Okay, so any questions on this? I see time we have 15 minutes. Actually, this is what we have just done. This is what we have just done. We have shifted X2, which is 1011, or sorry, 101 into that, which is 101 after 4 pulses. So I usually like, after 3 pulses, I usually like to add here something called pulses, but here they have said before pulses applied, so initial, after first pulse, after second pulse, after third pulse. Now, when you do this thing, you don't need to put the arrows the way I've been doing it. You can just do something clean. For me, I know what you're doing. But I use arrows here all over the table to just show you how this is being done. So you can do this in your own rough work, but once you get the hang of it, it becomes very easy. Okay, actually today I started my slides here. So it's funny we've not reached there. But we have seen shift left operation, and we have seen, something about shift left. So we've seen here that actually you can shift left. We've seen that basically the information is shifting in the right direction, but we can also arrange our shifting to move in the left direction. It wouldn't change anything. It is just, yeah, there's nothing there. The connections are the same. The other thing is that parallel versus serial. So parallel is clearly faster because the information is transferred in one go, but it requires more connections, okay? So for you to do parallel transfer, for instance, between this register and that register, if it's a 4-bit word, you need 4 lines so that you have this flip-flop transferring to that flip-flop and so on. Whereas with shift register, you can have your 2 registers here with 1 flip-flop, 2, 3, 4, and 1, 2, 3, 4, and you just have 1 connection. Here you need 4 connections. I usually tell you, I remember teaching you about this in the first part of the lecture, of the course. And I said, if you've opened the desktop and looked at the motherboard, there are those buses. So those are really for parallel data transfer, the buses where you have many cables together. Even your Ethernet cable is a parallel data transfer. If you've ever crimped a cable, you know the wires that are in there. But for remote transfer is where you're transmitting information over a longer distance. It is probably better to do it in shift, serial, rather than parallel. The reason is because you would have so many cables strung along very large distances, which can be expensive, whereas here in serial, you would need just one cable and your information will move. So in other words, usually, sometimes you can combine these so that you can take advantage of the simplicity and cheapness or economy of the serial transfer, and also the speed of parallel transfer. But generally, parallel is faster. Unfortunately, it requires more connections. And so it doesn't work nicely for parallel for long distances because of the economic cost. Serial transfer is slower because you're transferring bits per, you're shifting information, so you need more clock signals. And so the number, if you're transferring 8 bits, you need 8 times more time than the parallel transfer. But it works better over long distances because it's cheaper, just one cable, and also uses fewer connections. Okay. All right. Okay. I sort of get your, yeah. I think this one, initially you can say that it is 0. Even here, you can say that it is not empty. It is, so if you want, you can start with D note here, you put D1 here, but it doesn't really matter. In any case, this one usually will not be in your table. But you just need to remember that when this pulse comes in, you need to already have your D note set, and it should have existed for as long as, at least as long as the setup time. Okay, so I have a small question for you. Okay. You shouldn't type your answer in the chat. So this is, assume the same initial contents of the X and Y registers. What will be the contents? What will be the contents of each flip-flop after the occurrence of the 6th pulse, shift pulse? Okay, so I don't know whether, let me put it there. I hope you can see that quiz. Emmanuel. Emmanuel is very scared. He's like, oh God, this is, we've just studied this. It is basically to give you some marks to thank you for attending. The poll is that's why I give 2 marks for attending and 1 for the poll, because I'm more interested and really rewarding you for attending. But yes, you do this poll. Please do it in 3 minutes, just 2 or 3 minutes. And if you cannot see it, I think there is a student who said that you should click on the poll icon and it will come. Guys, I don't see many of you doing this. I'm about to stop this thing. 1 minute to go. I like our progress on this course. Unfortunately, it feels like this semester is very short, so it's good that we are doing it online because we can move faster. But I think we'll be fine. So I would like to tell you that although there are so many different answers, I'm getting people, at least ticking each choice, meaning that some people are failing this. But that's okay. That's not the point. That's the point, is to be able to by the way, I have Daphne. I have 200 students. 205 students, I think, did the test. But I teach about 130. So I need to add more marks to these small quizzes that I give. Okay, so about 123 of you have participated. I need all of you. The last 5, please, the last 4. Okay, I have to end the quiz now because we've reached 3.5 minutes. Okay, I'm going to share the results. And as you can see, the vast majority have chosen 000, which is the right answer. So 64% of you have passed it, 000, and the rest have not. All the other answers are wrong. Basically, actually, if you noticed, I made a mistake because the last answer and the first answer are basically similar. Anyway, the answer was 000. Elian Maleka. You guys. So the reason why that is you can see that if you add another 3 pulses, this will continue to be 000. But actually these zeros will now go and push out these, and you'll end up with 000. And that's a consequence of this 0 at the input. So basically when we deal with this, sorry? Oh, you can't see you can't see my screen. Okay. Just a small explanation of what we are doing. Okay, so we can, yeah, so I was saying that the reason why, so yeah, I was saying that my pencil thing is hanging, so just give me a moment. Okay. Okay. So I was saying, just 1 minute, that after this, the reason we have a 0 here. So every time we clock, you input a 0. That's why after three pulses, you have zeros in a X register, and your information which was originally in the X register has actually been pushed here. Now, if you give 3 clock pulses again, the same zeros will appear here because they keep going in, okay? So 0, 0, 0, but what happens is that they push these ones out, and these ones simply continue into the Y register, meaning you still end up with a 0. So that's a consequence of the fact that this is always kept at 0. So the answer was after 6 pulses and above, even if I had said 10, even if I had said 100, until we change this, everything will then be 0. So we need to remember or to know that, okay, I have this information, I need 4 pulses, and after that I need to stop, and my information will be pushed into the new register. Okay, Joel, what if D is 1? If D is 1, then all this would be 1. You see, this would be 1. And after 6 pulses, you would have 1, 1, and 1, 1. Okay.
Sir,
And then I missed the quiz. Yes.
I was asking, what if there are only 2 registers? Where does that information go?
These are 2 registers.
It's impossible.
But these are 2 registers. So what do you mean, what if there are 2 registers?
Because the input 0 was pushing our information until it was shifting it, not so?
Yeah.
So now, where is it shifting to?
You're meaning, oh, so
the 101, where is it going?
Like here. Remember that even Y had information, it was 0, 0, 0. So every time we were shifting, these zeros were getting discarded. Remember when I was saying discarded? In general, because our network stops here, we just say it is pushed out. It just gets lost. But in reality, usually that information goes into some other part of the circuit. Okay. Okay, so I hope you've understood that, Joa. Okay, so let's end here. Wednesday, so we will meet again on Wednesday next week. Can I say that we do an exam we do an exam. How is next Wednesday for an exam?
It will not be fair for some of us.
Why?
Next week, so
we have some engagements. I have some official engagements on Thursday, and that next week, Wednesday, I'll be out.
When you say engagements, do you mean like a wedding party you want to attend? What do you mean? Like, I want to understand.
No, I'm supervising some project in Arua, and we have a progressive meeting on that day. So
you are going to Arua?
Yeah.
So you're going to Arua? Oh, okay.
Yes, sir.
Kasiswa, okay. You gave us an assignment. Yes, Ndajira, I know I gave you an assignment. That doesn't mean you can't do the test. The test is and assignment are totally different things. Okay, so when does this semester end? When do we stop? When do we break off for Christmas, guys?
They haven't given any official date for breaking out for Christmas, but what we know is exams will be starting in the first week of January.
Kasasra has said that he is not ready. Don't say we are not ready, because it might be only you. You are the others are ready, Kasasra. You can come next year and redo this course, so that's okay. We always offer every time. I see multism assignment. Yes, Ndajira, you know I gave you multism assignment, but that has nothing to do with the test. And anyway, you are doing it as a group, so I don't think that I'm not over, like I'm not giving you too much load. So don't worry, I'm trying to be considerate. Okay, so if we cannot do 15th on Wednesday next week, let us tentatively plan for 20th of December, which is a Monday. Okay. But I think if we are not going that far, then we have to figure out how we do that test next week. Maybe on a Saturday. We'll have to see. I'll talk to my boss and we agree on what we can do. Otherwise, we end at exactly midday. I'm not taking any time from you. Have a nice week. Please work on my assignment, which I think is due this week, if I'm not mistaken. And by the way, I hope you have multism. If you don't have multism, do let me know. But I've been using it for years, so people have it. You don't have?
Yes, we don't have it.
But now, if you don't have, what were you going to do? You should have told me the day you saw that thing. But okay. I'm going to give you a copy that does not require a license. I'm going to put it somewhere. I'll give it to one of the class reps and you can get it. But yeah, we want to do this and we want to do it physically. I know some of you are about to break off for Christmas, but you know this is unprecedented. We are studying in COVID times, so we need to make some adjustments. And if you don't want to do it close to Christmas, you can do it on Monday next week. I don't have a problem. I can set a paper for you for Monday next week. Jordan, when is the hand-in date for the assignment? Is it Friday?
It was not communicated.
It is not on the paper. I'm sure it's on the manual. Look. I think I communicated it. So anyway, if it is this week, it's on 15th. Yeah, but 15th is still far away. Why are you scared? 15th is still a whole week away. It's okay.
Excuse me, sir. You have to first study that thing, how to use it. Go and watch tutorials on YouTube, learn how to use it.
I've given you a tutorial. I've given you a tutorial. And by the way, let me tell you, Maurice, you can do all that stuff in like 5 hours at night. Just start at 10 p.m. I know you guys don't want to work. Start at 10 p.m. By 2, you'll be an expert on multism. Remember, I'm teaching this stuff. I know over the years I've given this. So I don't think that is an excuse. For now, let us keep it at 15th. Okay. And in the lecture on 15th, you can tell me how things are and I will advise. But you cannot tell me that you have a weekend coming up. I mean, what do you guys do? You have a weekend coming up and you're saying you need 2 weeks to study multism, yet I've given you a tutorial and the tutorial is enough. You don't even need to go to YouTube, but you can if you want. I don't have a problem. Okay, so let's end here. Have a nice week and take care.
Nice week too.